integral for continuous time LTI systems, okay, or linear time invariant systems. Now, if you recall from the past video or part 13 of lecture series, we consider xt as a sum of scaled and shifted version of the basic pulse signal, delta of del t. Now, this pulse was having an infinitesimally but finite duration t, okay, on the axis t time. The duration was delta, okay, and the height was 1 over delta, which means the area of this pulse is unity. Okay, so this pulse was defined in terms of its weight or the area, that is the area is still unity. Okay, so the height is 1 over delta and the duration is also delta. Okay, and if you can recall, what we discussed last time was that as a limit, um, if you view this scenario where delta or the width of the pulse approaches 0, okay, then this whole thing becomes the definition of the continuous time impulse function delta t, okay, and delta t is also defined in terms of its weight. So it does not exist where t is not it's 0 where t when t is not equal to 0, okay, at t it's undefined, but delta t dt is unity. Okay, so just like the discrete time sequences which can be described or they can be decomposed into unit impulse sequences, xt can also be approximated in terms of pulses. Okay, so and this approximation again, it becomes better if uh, this finite duration delta, this small duration delta becomes small. Okay, so this approximation becomes better. It resembles more towards it approximates better the original signal when this duration is small. Okay, so in particular, the approximate representation in the following equation represents the signal xt as a sum of scaled, okay, and shifted version of the basic pulse delta of t. So these the scales are basically the amplitudes of the signal at that particular time instant. At that particular time instant, so you see this t is the time, okay, and since you are taking k delta out of it, t delta represents the finite duration of the pulse, k is integer, so k delta is again time, okay. So k delta is the value, it's the time, and then x of k delta represents the amplitude of the signal at the time instant k delta. Okay, an interpretation is shown over here. Okay, so for example, this black line, solid line, represents your xt, which is the continuous time signal. Okay, and x hat t represents a staircase approximation. So what you are doing over here is you're approximating the continuous time signal in terms of the pulses, and these pulses are evenly spaced. So you have 0 to delta, this is the first pulse, then you have twice delta, okay, then 3 delta, so on and so forth. So this continues, okay, up until k delta. So if you sum this up, this is the expression. Okay, so x of t can be approximated by x hat of t in terms of delayed, and scaled impulses. Okay, so for example, the first staircase over here, the first staircase is for k equal to 0, and this term, if you expand this term, or if you expand this term, or if you see it from the graph over here, this is basically the value of the signal at time instant k equal to 0, and this is then delta of del t, right? This is delta of del t. Similarly, if you look for the second staircase, this over here represents x of delta, where k is equal to 1, so this is x of delta, whatever is the value at x delta, basically over here. Okay, multiplied by delta of del t minus delta. Okay, multiply by, so it has to multiply by delta. Okay, that's how the function is defined. Okay, so you go on expanding this for the all for k's greater than from 0 to infinity, and for example, for the third one, this will be x of 2 delta. Okay, whatever is the value at 2 delta, or the k is 2 over here. So the weight of the shifted pulse is 2 delta multiplied by del of again delta, k is 2, so this becomes t minus 2 delta. Okay, And if you sum this up, for k ranging from 0 to infinity, well, this is the this becomes the approximation x hat of t. Okay, so if you sum all these staircases, and this sum basically continues over k, then this is an approximation that approximates the continuous time signal. This approximation is x hat of t over here, which approximates the continuous time signal xt, right? And you can see from the graph as well, if you are going to decrease the width of this finite duration pulse delta, if delta is going to approach to 0, it's a very short duration pulse, then your approximation of x hat t is it's going to resemble more and more that of xt. Okay, that means if you take an absolute difference, you define the error as xt x hat t minus xt. Okay, so if you, for example, if you define an error like this, then this error is going to reduce for very small length pulses when the delta approaches 0, okay, or a very short duration pulse. So this error is going to reduce. Okay, so this error is going to decrease for as delta approaches 0. All right. So okay, now this is an approximation of the signal xt. Okay, so consequently, now the response yt of a linear system to this signal will be the superposition of the responses to the scaled and shifted version of delta t. So what it means is, since we are talking of linear systems, now the response of the system, for example, now what we have done is we have visualized xt in terms of an approximation, which is defined in terms of scaled and shifted pulses. So the response of the system, for example, the response of the system for the if you consider the first pulse only over here, okay, this is x0 and the weight is x0, okay, multiplied by delta of t, this is the pulse. All right, so the response of the system, if you consider over here, is x naught h naught t. H naught t is the impulse response. This is the impulse response for delta of delta t, because k is 0 over here, okay, and that represents k 0, and then t, and then this is multiplied by delta. Similarly, this is the first pulse. Okay, so we are talking of this pulse over here, and this is the response. Then again, you take the next pulse. Okay, and this is the weight of that pulse is x delta, and the response to the system is x delta multiplied by h delta of t. Okay, where k is 1. So over here k is 1, over here k is 0. Okay, then again you continue doing that, let's say for k equal to 2. So we have basically three pulses over here. Again, this is for k delta. So this is not k equal to 2, this is basically k. Okay, so the response is again xk delta, where k delta represents the value of, or the amplitude of the signal at k delta, multiplied by hk delta t. Now if you add them up, if you add all of those, then this can be expressed as a summation. Okay, so since the system is linear, then what you can do is the response to one pulse can be added to the response that you get for another pulse. Okay, and then you keep on adding for up until k pulses, and you can approximate your output. Okay, that's the idea. So you see the response yt of a linear system to the signal will be the superposition of all such responses. So it will be the superposition of the responses to the scaled and shifted version of delta t. So specifically, if we define hk delta t, okay, which is again an approximation, the response of an LTI system to the input to the pulse. So this is the response hk delta t over here to the input xt delta t minus k delta. So for example, for k equal to 0, this will be h0t, and that the input will be delta t. Right? So you see over here, this is exactly what has happened. For k equal to 0, this is h naught of t. For k equal to 1, this is h delta of t, because this is k is equal to 1 over here. Okay, so you can see what is going on in here. Then for any arbitrary k, if this is xk delta, then the response is also scaled by the same scalar. Okay, but the pulse was at k delta, So therefore, at k delta, the impulse response is given by h hat of k delta t delta. Okay. So these are the individual responses towards the pulses having the same finite duration delta, but these pulses are occurring at different instance in time. So since they are occurring at different instances in time, for example, this pulse occurs at k equal to 0, then this pulse happens at the time t equal to delta, and then this happens at t equal to k delta. So you have to add them up because the system is linear. If you add them up, for example, you go on adding these responses, okay, add this up. So the result will be precisely y hat of t, okay, which is basically expressed as a summation in this equation. Okay, so this is what it says. So then from the superposition property for the continuous time linear system, we see that y hat of t is basically superposition of the scaled impulse responses of the system. That follows from the linearity. So the interpretation of the above summation is very similar to that for the discrete time case that we have seen previously. Okay, so again for a discrete time case, the convolution sum was in terms of, if you recall, these were the scaled impulse responses which you were summing up, right? So if you introduce an impulse, the whatever is the response, we called it the impulse response at that particular instant of time k, and if it is scaled by, let's say, xk, the impulse response is also scaled by xk, and then you have to add them up. Okay, so for each impulse response at index k, you have to sum all these responses to produce y of n. Okay, so this is a very same situation is over here. Okay, so for a finite duration delta, this is the scenario that the output is the superposition of the scaled and shifted versions of your impulse responses. Okay, now the visualization of this approximation to an LTI system as an input produces an output. Okay, so this is what you've introduced to an LTI system, and that's the output, y hat of t. So y hat of t is basically the summation of all such responses to the pulses at 0, at delta, at 2 delta, 3 delta, or up until k delta. Okay, so you are adding them up. This follows from the superposition, and this xt is as a limit. If you This is basically the limit where delta approaches 0. Delta is approaching 0 for the approximation of x hat t. This becomes xt. Okay, and therefore yt is also the same approximation if you consider the response of the system for a very short or for an infinitesimally small duration pulse, okay, which can be considered as delta t. This response becomes equal to yt, which is the original response of the system. Okay, so this is the graphical interpretation of the response of the continuous time linear system. So basically it is emphasizing on the linear system or the superposition of the individual scaled impulse responses. Okay, because since we express x hat of t, which is the approximation of xt in terms of the delayed and scaled impulses, then the response is also in terms of the response over here is also in terms of the scaled and shifted impulse responses. Okay. Okay. Now, you see in figure 2.15a, okay, this is the interpretation of what is this happening in this figure. So 2.15a is showing the approximation of x hat of t, and then you have the continuous time signal xt, and the other three figures b, c, d are three pulses towards which are introduced to the system independently, and then you have the outputs, and you are summing them up. Okay, so you have the impulse responses at that particular instance of time. For example, this time is t equal to 0, this time is t equal to delta. So you see the subscript of h are 0, delta, and then subsequently you have k delta, so therefore it is k delta over here. So this is linearity. Okay, so figure 2.15a shows the depiction of xt and its approximation x hat t, while in figure 2.15bd it's shown the responses, shows the responses of the system to the three weighted pulses in the expression for x hat of t. So these are three weighted pulses in figure b, c, d, and their responses. Okay, and then the output y hat of t corresponding to x hat of t is the superposition of all these responses. This is shown in 2.15e over here. Okay, so again, this is the approximation for y of t, which is the original output of the system. Okay, this response is it's the response towards x hat of t, because x hat of t is the approximation of xt in terms of the weighted pulses. Okay, these are not the delta t functions, so you don't have this continuous time original response over here. This is just an approximation. Okay, so when what remains then is to consider what happens when, well, delta becomes vanishingly small. So we have already talked about this, that is that in particular x hat t becomes an increasingly good approximation to xt. That is, in fact, the two will coincide when delta is equal to 0. So you see over here xt, x hat of t becomes equal to xt if the pulse duration is small enough, is vanishingly small enough. So this becomes the delta function. Okay, this becomes the delta function. Naturally, if you're considering a very small pulse duration signal, then you're not going to sum up infinite amplitudes, a continuum of amplitudes. And the natural extension of summation, it becomes an integration. Okay, it has to become an integral. So it becomes an integral if the pulse duration is very small. Basically, what it says is it will become an integral. So you can express your xt in terms of weighted and shifted impulses like x tau delta of t minus tau, where delta t is the impulse function in continuous time domain. Okay, dt, right? You can see the equivalence because because this delta function exists at t equal to tau. Okay, well, the integration variable, you can consider this as tau. Okay, so you can take xt out of this integration, and then this integration will produce a weight or the area equal to unity, because under the integrand it's the delta t function. Okay, so it's indeed equal to xt over here. Okay, so the approximation becomes better if the pulse duration is very small. So in that sense, the pulses are the delta functions. Okay, so consequently the response x hat t, namely y hat t, the response which is y hat t, must converge to yt, that is the response to the actual input xt, as illustrated in 2.15. So this only happens when you consider a very small or a durations pulse which is inconsequential for the practical systems, right? So it becomes the delta function. Now, so furthermore, as we have said, the delta small enough, the duration of the pulse is of no significance in that as far the system is concerned, because the response to this pulse is essentially the same as the response to unit impulse at the same point in time. Okay, you see, the idea is whatever duration of pulse you are considering, you're going to have a response. Okay, you're going to have a response. For example, over here, this is h naught of t, and this is h delta of t. So wherever in time that pulse is occurring, okay, you're going to have an impulse response. This impulse response is at k equal to 1 or delta. This impulse response is at k delta. Okay, this impulse response is at 0. So wherever the pulse is occurring, you are having an output. Okay, and that output is also scaled, right? So basically, for the system, it's none of its concern whatever is the duration of the pulse you are considering. Okay, it's just the approximation that is getting better with the short duration pulses. Okay, because we have a better approximation for xt. Therefore, xt is going to lead towards y of t. Okay, so that is, since the pulse corresponds to the shifted unit impulse, as delta becomes increasingly small, decreasingly small, the response hk over here, the response hk delta t to this input pulse becomes a response to an impulse in the limit. So that in the limit becomes the response to the impulse function delta t. Okay, so therefore, if we let the ht subscript t tau denote the response at time t to the unit impulse which occurs at t equal to tau, located at time tau, then yt is given as such. So this is again the natural extension of yt. Well, you are considering this to be a very short duration pulse. Therefore, you have to consider and integration, that is the area under the curve. Okay, so again the weights are x tau, and since the pulse is occurring at t equal to tau, pulse is non-zero at t equal to tau over here. Therefore this becomes your instead of xk delta, you consider t equal to tau where the pulse exists, and h tau of t is the response of the system to delta t. Okay, so ht is basically the impulse response of the LTI system. Okay, and note that tau becomes now the variable of the integration. Okay, so as delta approaches 0, the summation on the right hand side becomes an integral. Okay, that's a natural extension, and as can be seen graphically in figure 2.16 over here. For example, you see over here there is only one. So for example, if you consider this summation, this represents again a finite duration pulse having the width of delta. Okay, this is k delta, k plus 1 delta, and then you are multiplying this pulse with the signal xt or x tau. Okay, and whatever is the amplitude at k delta becomes the weight, okay, of this pulse, and the response of the system to the pulse will be the same scale, with the same scalar xk delta multiplied by hk delta t delta. Okay, so that's the response. Otherwise, I mean, this pulse occurred at k delta. Other than that, whatever is the value of x tau, we are not interested. It's 0. Okay, so it only occurs at k delta. Therefore, it has to be scaled by the amplitude of the signal at that particular instant in time.